Hubble's astonishing discovery of galactic redshift, that all distant galaxies are speeding away from us, had startling implications regarding the origin of the universe. In fact, it now appears that the universe began at an instant of time approximately 14 billion years ago, and it's been expanding ever since. Lecture 32 tackles a really big question. How did the universe begin? This is the ultimate origin question. And I've organized this lecture into two parts. First, after a brief consideration of the philosophical implications of this question of universal origins, I'll spend a few minutes trying to give you a sense of the unimaginably immense scale of the universe. You know, it's important when throwing around ideas like galaxies and clusters of galaxies to get a sense of how large these objects really are. And then in the second part of the lecture, I'll introduce the scenario of the origin of the universe called the Big Bang. I'll do this in three steps. First, what was the Big Bang really like? And it turns out that it wasn't really like anything that we can easily imagine. Then second, what's the evidence for this origin events? I'm going to introduce three lines of observational evidence: universal expansion, the cosmic microwave background, and the distribution of light elements. And then third, I'll examine some of the astonishing discoveries related to the Big Bang. These discoveries include estimates of the age of the universe and the realization that much of the universe's mass is invisible, and then various predictions about the ultimate fate of the universe. You know, the past 100 years of astronomy have been characterized by an ever-expanding view of the size of the universe. First and most obvious, the things we see in the heavens are many, many different kinds of stars, billions of stars along the main sequence from brown dwarfs to supergiants. Those are the hydrogen-burning stars, and then we see red giants and we see white dwarfs, which add to the whole variety of stars. And thanks to the efforts of Henrietta Leavitt and Harlow Shapley on Cepheid variable stars, we learned that some of these stars in our own Milky Way galaxy are more than 100,000 light years away. Our own home contains hundreds of billions of stars in an immense spiral galaxy. And then Edwin Hubble, he discovered that there are countless other galaxies and other clusters of galaxies well outside the confines of our own Milky Way. Some of these objects turn out to be many billions of light years away. And Hubble also made the astonishing discovery of the close relationship between a galaxy's distance and its velocity away from us. That relationship was given by a simple mathematical law called Hubble's law: velocity equals h times distance, where h is the Hubble constant. Hubble's results immediately opened a whole new realm of scientific inquiry. For one thing, it provided a distance scale based on the spectroscopic redshift of galaxies. That's a scale that works for virtually any object we can observe. But Hubble's law does something else, and that's even more profound. For the first time, astronomers had an observational method to study the origin of the universe. Before Hubble's observations, any discussion of the origin of the universe was purely philosophical speculation. Even though this is a series of lectures on science, it's really fascinating to think more about this philosophical side of the origin question. Think about that question. How did the universe come to be? What did your philosophy or your religion or your intuition tell you about that question? Do you even care how the universe began? Well, a lot of astronomers cared, and some of them were quick to debate the matter even without any relevant observational data. Now, some astronomers believed in biblical accounts of God's creation. The influential cosmologist and Catholic priest Georges Lemaitre, for example, he was absolutely committed to an origin event. He was a Christian. These scholars believed in a moment of creation, and their cosmology had to conform to that belief. And now other scientists, such as the avowed atheist Arthur Eddington, preferred a steady-state universe with no beginning. To Eddington, a moment of creation was simply an unnecessary complication in describing the history of the universe. So think about that. If there was no observational evidence, which side would you have supported? Steady state or an origin event? Now, the dramatic advance made by Hubble is that his data provided reproducible observations that pointed to an origin scenario that was wonderfully simple. And of critical importance, the origin scenario was also testable. So before examining this evidence for the origin of the universe, let's take a few minutes to think about the scale of objects in the universe. You know, I've been tossing around terms like stars and galaxies with ease, but it's difficult to imagine the physical scale of these objects. So I want to take you on a journey of increasing scales of the universe from the comprehensible realm of everyday objects to the incomprehensible scale of the cosmos. And I'm going to do this by starting with this cube-shaped box. This box is 1/10 of a meter. That's about 4 inches on each side. So this box could hold, for example, a grapefruit or a softball. And in order to get a handle on the scale of the universe, I want you to imagine successively increasing the length, the width, and the height of this box by a factor of 100 at a time. That means that each new larger box in this sequence will hold 1,000,000 times the volume of the previous one. That's because 100 times 100 times 100 equals 1,000,000. Okay, so the first larger box is 10 meters. That's about 33 feet on each side. Such a box would fit around a small 2-story building. So that's a pretty comprehensible size too. Now, each increment I'll talk about bears the same relationship to the previous box as a 2-story building does to this cardboard box. Now, a second increment of 100 brings us to a cubic kilometer. And that would hold a small town or many college campuses, as well as a significant volume of the ground below and the air above it. But you can easily see such a volume, and you can comprehend that volume in everyday terms. And okay, the third increment is a cube, 100 kilometers on each side. That volume's large enough to encompass most urban areas, for example, the greater Los Angeles area or the New York metropolitan area, or even the area around Washington, D.C. Beltway, that would fit into such a box. Of course, the box would also hold a significant chunk of the Earth's crust and up into the highest part of the atmosphere. Most of us move around in an area on the order of 100 by 100 kilometers on a regular basis, so that's also pretty comprehensible in size. But the next increment goes from 100 kilometers to 10,000 kilometers on a side, and that's a big jump conceptually anyway. A 10,000 kilometer cube would not quite hold the entire Earth, because the Earth's close to 13,000 kilometers in diameter. Now, I don't know about you, but that's about as big a distance as I'm comfortable with. I've flown about 10,000 kilometers from Washington to Hawaii, but that's a long way to travel for a human. And so then you come to the fifth increment, and we come to a box that's 1,000,000 kilometers on a side. That box would hold the Earth and the full orbit of the Moon. The Moon's orbit is about 770,000 kilometers in diameter. Now, alternatively, this box would hold the entire Sun quite nicely. So these first 5 increments represent a factor of 10 billion in distance, from 1/10 of a meter to 1,000,000 kilometers. That range encompasses the extreme distances that humans have journeyed. Astronauts have been to the Moon and back. Such distances are almost comprehensible, but we have to go a very, very long way to complete our exploration of the whole universe. We're beginning to approach these epic distances where it's easier to speak of distances in terms of light. So I've been using this concept of light distance, but what does that mean? Light travels about 300,000 kilometers in a second. So 300,000 kilometers is a light second. So you see, this is actually a distance. Then we can just do the multiplication. In 1 minute, light travels about 60 seconds per minute times 300,000 kilometers per second, which equals 18 million kilometers in a minute. So 18 million kilometers is a light minute. Then there's 60 minutes in an hour times 18 million kilometers per minute. That's 1.08 billion kilometers in an hour. That means that 1.08 billion kilometers is a light hour, and you can continue with this logic. 24 hours per day gives you 26 billion kilometers in a light day. So a light day is 26 billion kilometers. And then there are 365 days a year times 26 billion kilometers per day. So it's 10 trillion kilometers in a light year. So we're into the realm of light distances here. And recall that the fifth increment took us to a box that held the Earth and the Moon. The next factor of 100 is a box 100 million kilometers, or about 6 light seconds on a side. Now this box holds the Earth and either Mars or Venus during their closest approach. The box can't quite hold all 3 planets. Alternatively, the box could hold the Sun and almost encompass the entire orbit of the nearest planet, Mercury, which averages a bit more than 500,000 kilometers away from the Sun. So this box is just a tiny part of the solar system. And then the 7th increment, that's a box 10 billion kilometers on edge, about 9 light hours on each side. And this is a huge volume. If it's centered on the Sun, it would encompass almost all the planets. And I find this amazing. The next box is about 40 light days on each side, and that box would encompass the entire solar system. The solar system in this sense includes all the objects that are gravitationally bound to the Sun. That includes comets and other objects much more distant even than the outermost planets. But this box includes virtually nothing else. the sun, the solar system, and nothing else. Then the next box, it's a little more than 10 light years on a side. That would contain the solar system and the brightest neighboring stars, Sirius, which is a white dwarf star. Actually, Sirius is a double star. It's about 8.6 light years away. The box would also hold perhaps 100 other less bright stars. Then the 10th box, 1,000 light years on each side. Though it encompasses only a very, very small portion of the Milky Way, it would include countless hundreds of thousands of stars. And so here we've come 5 increments from the scale of the Earth and the Moon. That's another factor of 10 billion in distance, and we're still only in the suburbs of the Milky Way galaxy. The distance across the box is less than 1% the size of the Milky Way galaxy, and we still have far to go. Now we're at the scale of entire galaxies. Most, though not all, of the Milky Way galaxy of several hundred billion stars would fit into the next box, which is 100,000 light years on a side. Actually, you could almost squeeze all the stars in if you'd have to squeeze it along the diagonals of the cube-shaped box, so the Milky Way galaxy would be at an angle. By the way, most of what would be missing in this box is a great deal of galactic mass that lies farther out, but isn't in the form of bright stars. It's hydrogen gas that you can't really see except with radio telescopes. Then the 12th box, 10 million light years on a side. It holds all the local group of galaxies and more, dozens of galaxies in all. And the next increment takes us to 1 billion light years per side and extends well beyond the local supercluster. This volume holds hundreds of millions of galaxies grouped in clusters as well as voids. And the voids are vast regions with very few galaxies. And now that's almost it. The entire known universe is only about a factor of 10 larger than that. Tens of billions of galaxies lie within this volume, which has a radius something more than 10 billion light years from Earth. And I can't stress enough that such a volume is unimaginable. I can tell you about these 14 increments of a simple box, and for a few increments your mind can probably comprehend the increases in scale. But we've gone from a grapefruit through almost 14 increments. That's more than 27 orders of magnitude increase in size, and no one, not even the cosmologists, can really comprehend such epic distances. Now, to the origin of the universe. Remarkably, observational evidence now suggests that this universe may have originated as a single tiny point in the distant past, about 14 billion years ago. And the universe has been expanding ever since. This theory that the universe came into existence at one moment in time has subsequently undergone rapid expansion. That theory is called the Big Bang. I'm going to review 3 lines of evidence for this. They are, first, the universal expansion of the universe as discovered by Edwin Hubble in the 1920s, then the cosmic microwave background of a constant static microwave energy that pervades the universe. That was discovered in the 1960s. And third is the relative abundance of light elements, hydrogen, helium, and lithium in the cosmos. First, though, let me try to explain to you what the Big Bang was like. And I have to admit this is an absolutely impossible task. It's impossible because nothing in our experience could possibly be anything like that origin event. In any case, the first step to imagining the Big Bang is to think about Hubble's discovery that galaxies are moving away from us. He found that the farther a galaxy is, the faster its motion is away from us. Everything in the universe seems to be expanding away from us. Now imagine playing a movie of this situation backward. If you played the movie backward for long enough, then all the galaxies would appear to converge back to a single point. Think about that reverse scenario. All the matter of the universe zooming back towards a common center, the more distant masses zooming in much faster than those close by. Closer and closer, all those disparate galaxies converge until, bam, they're all back together at a point. That's the Big Bang played in reverse. So, what was this Big Bang really like? First, think about what it was not like. In spite of its name, the Big Bang was not an explosion in which matter expanded into an existing space. Okay, this is a really critical point. There was no space before Big Bang. There was no universe. There was no existing volume. The matter didn't expand into an existing volume because the universe didn't exist. So the Big Bang was the origin of volume itself. It was the origin of space and matter and energy and time. The universe simply became. And then it became larger and larger. Existence expanded itself, not into anything. Everything expanded. There was no inside, no outside. Now, this is a totally foreign concept, so don't be frustrated if you can't imagine it. But I have to emphasize again, the Big Bang was not an explosion. So what was the Big Bang like? Now, the surface of an expanding balloon provides one helpful analogy. And I want you to imagine yourself as a two-dimensional being, a completely flat being on the surface of a balloon. You can move to any point on the surface, but you have absolutely no concept of a third dimension. Now imagine what it would be like if the balloon started expanding. There you are, a point on the surface. Any other point on the surface is moving away from you as the balloon expands. The farther away the point is, the faster it's moving away. That's just like Hubble expansion. But from your two-dimensional point of view, the balloon doesn't expand into anything. The balloon just gets larger. Now you can try this yourself with a balloon that has markings on it. I put a bunch of dots on this. Now watch what happens when I blow this up. See, the two-dimensional area of the balloon gets larger. If you were a two-dimensional being on the surface, you'd perceive the same kind of expansion as Hubble saw in our universe. The problem with this analogy is that you have to imagine yourself as a two-dimensional being, but we all actually know that the balloon is expanding into a third dimension. Unlike the balloon, our universe isn't expanding into anything, at least not into anything that we can perceive. Another analogy for the Big Bang is provided by large batches of raisin bread dough as it expands and rises. Look at this. From the point of view of the raisins in the raisin dough, all other raisins are moving away. Furthermore, more distant raisins move away faster because there's more intervening expanding dough. But there's a problem with this analogy as well. Any mass of raisin dough has an obvious inside and an outside, but the universe has no outside. It isn't expanding into anything. And there's another point. In these analogies, the Earth doesn't occupy a special place in the cosmos. According to the Big Bang view of the origin of the universe, all observers anywhere in the universe see exactly the same sort of expansion. Now, this is also somewhat of a philosophical point. Most astronomers believe in a homogeneous universe. That's a universe in which, at least on a large scale, all places are similar to all other places. All places have the same natural laws. They have the same universal gravitational constants. They have the same charge on an electron and so forth. But think about it. There's no reason why the universe has to be this way. Perhaps some places are closer to a center of sorts. Perhaps the gravitational constant differs with distance from this center. You see, there's simply no way to test this idea of homogeneity, at least not at present, since we can't journey far away. There's no way that we can test natural laws billions of light years away. In the meantime, homogeneity remains an untestable assumption of most cosmological models. Okay, now to the actual evidence for the Big Bang. As I've said, there are three types of observations, and when they're combined, they provide compelling evidence to support the Big Bang theory. First and foremost are the numerous observations of the universal expansion of galaxies. This was Hubble's greatest discovery. The galaxies are speeding away from us, and that the farther the galaxy, the faster it's receding. Hubble based its conclusion on measurements of Cepheid variable stars as his distance scale, and then redshifts of characteristic absorption lines, and that measured the velocity of recession. Hubble only measured about 20 galaxies in his initial work, but that number has been increased to many thousands by subsequent astronomers. So we have compelling evidence that the universe is expanding. However, I have to stress that expansion alone doesn't prove the Big Bang. See, it's possible, for example, that the universe is in a steady state expansion with new matter materializing, continuously forming new galaxies as old galaxies get farther apart. Think about that. You could have a steady state universe with no origin moment and still see expansion. So as cosmologists grapple with the strange consequences of universal expansion, they divided themselves into two camps. There were the bangers and the anti-bangers. Georges Lemaitre, the Catholic priest, naturally favored the Big Bang model. And he wrote that these considerations, besides providing a natural beginning, supply what he called an inaccessible beginning. In other words, the Big Bang left the door open for a divine act of creation. And then there was the anti-banger, Arthur Eddington. He was the atheist. He saw the expanding universe as evidence that new matter, new stars, new galaxies were constantly being created in the universe. He wrote philosophically that the notion of a beginning to the present order of nature is repugnant to me. That's the way he put it. So expansion by itself couldn't resolve this issue of the origin of the universe. So along comes a second compelling piece of evidence. That's the universal background of microwave radiation that appears to pervade the universe. The cosmic microwave background was discovered in the early 1960s by two researchers, Arno Penzias and Robert Wilson. They were at the AT&T Bell Labs in New Jersey, and they were working on satellite communication using microwaves. So they developed new high-sensitivity receivers, and right from the start, they experienced a high level of noise or static in their machines. They tried everything to get rid of this annoying static. At one point, two pigeons took up residence in the cone-shaped antenna, and in the words of Penzias and Wilson, they coated part of the dish with what they called a white dielectric material. They thought that might cause the disturbance. It was just by chance that a young astrophysicist, P.J.E. Peebles, who was working at Princeton University, heard about the problem and realized that what Penzias and Wilson had discovered was exactly what theoretical astrophysicists had predicted, that the microwave static was actually primordial electromagnetic radiation left over from the Big Bang. Now, this is an amazing concept. Think about it. At the moment of the Big Bang, the universe was flooded with highly energetic electromagnetic radiation. And as the universe expands rapidly after the Big Bang, the universe began to cool, and the wavelength of that electromagnetic radiation was stretched out to lower and lower energy. And the background microwave radiation we see today represents the remnants of that initial intense radiation. It's been stretched out to microwaves, which have wavelengths in the order of a foot long or so. Penzias and Wilson, they won the 1978 Nobel Prize in Physics for this discovery. And by the way, studies of cosmic microwave background have really intensified. Astronomers find that the background is highly uniform in all directions of the sky, but there are also subtle variations that may help us to explain why today's universe is so lumpy with these immense clusters of galaxies and even larger voids. And then the third line of evidence for the Big Bang is somewhat more subtle. As we'll see, the lightest elements of the periodic table condensed out of the Big Bang. While almost all this matter was in the form of hydrogen atoms, there was a small amount of helium and also a little bit of lithium appeared near the beginning. And if you measure the relative amounts of these light elements, it provides strong evidence of the Big Bang. Especially important in this regard is the ratio of hydrogen 1, that's normal hydrogen, to hydrogen 2, the isotope deuterium. Now we're going to come back to this point, but suffice it to say that the observed ratios of light elements closely match the predictions of a Big Bang origin. Now, in the final third of this lecture, I'm going to focus on three great mysteries about the universe: its age, the nature of dark matter, and its ultimate fate. Now, first, let's ask, how long ago was the Big Bang? Evidence for the Big Bang leads us directly to an answer to this question. You should be able to look at the universal expansion and by playing that tape backwards, so to speak, figure out the age. And in fact, the age should be directly related to Hubble's constant. If objects far away are receding fairly slowly, then the universe is older. But if those objects are racing away faster, then the universe is relatively young. And that sounds pretty simple, doesn't it? But it turns out this measurement isn't so easy because of that maddeningly simple problem, dust. You can't be sure of distance because we can't tell how much dust is in the way. Now, dust doesn't affect the redshift at all, so we have a good handle on how fast galaxies are moving away. But dust makes objects seem farther away than they really are. The more intervening dust, the greater the apparent distance to the galaxy. And since the object appears to have traveled farther at a given speed, the universe appears to be much older than it actually is. If we assume no intervening dust at all, then the universe appears to be no more than about 10 billion years old. A few years ago, this was the value favored by one team of astronomers led by the Carnegie Institution of Washington's Wendy Friedman. Now, assuming a reasonable amount of dust, another team of astronomers, this one led by Carnegie astronomer Alan Sandage, who worked just down the hall from Friedman, he estimated an age of the universe at about 20 billion years. And this is pretty amusing. You've got two leading experts in the subject of the universe's age. They worked in the same lab, on the same floor, down the hall from each other, and they were in total disagreement. And this friendly conflict became known to the press as what was known as the Hubble Wars. Now, the shorter age preferred by Friedman's group had a really severe problem, because it turns out that some individual stars in the universe are estimated to be at least 11 to 12 billion years old. So how can a star be older than the whole universe? Well, recent refinements of the age by both groups are gradually converging on an age of about 14 billion years. That's the current best guess, within a billion years or so. So it seems that for now the Hubble Wars are over. Measurements of the redshift of galaxies reveal all sorts of additional surprises that point to new mysteries. Look at this. Galaxies are gravitationally bound groups of stars, so they rotate about the massive central bulge. Seen on edge, one limb of a galaxy is rotating towards us and one limb away from us. So the redshift varies slightly from one side of the galaxy to the other side. In the 1970s, Carnegie Institution astronomer Vera Rubin was engaged in a methodical study of these galactic motions. Even in post-war America, by the way, it wasn't so easy for a woman to be an astronomer. She tells me a story about a gruff senior astronomer who spotted her in the lunchroom of an observatory facility, threw down several pages of handwritten manuscript and said, "Type this up when you get a chance." Because the male astronomer just assumed that a woman had to be a secretary. Well, anyway, Rubin's work was conducted at Kitt Peak Observatory in Arizona, and it was tedious. It took 3 hours to record the spectral data from one galaxy. And so on a good night, she'd maybe be able to observe 4 galaxies. But after a few nights, a curious pattern emerged. She expected the rotation speed to drop off at the outskirts of a galaxy where the mass was less concentrated. Instead, rotation speed turned out to be constant even to the outermost reaches of the galaxy. Now, the problem of orbital dynamics requires a very straightforward application of Newton's second law. Force equals mass times acceleration. All you need to know is the amount of mass in the galaxy and its distribution in space to predict orbital velocities. The mass of a galaxy can be estimated from the total number of visible stars. That gives you the mass, and we know the average mass of a star, and you get the size and brightness of a galaxy. And the distance of the galaxies are known from standard candles, so that information should be sufficient to calculate the rotation of the galaxy. But Rubin observed that the galaxies appear to be rotating 2 to 3 times too fast, especially in those outer regions. In other words, the force exerted by gravity was much too large based on the visible mass. Rubin had discovered that a significant fraction of every galaxy's mass is missing. This situation became even more complex when astronomers began to use radio telescopes to map atomic hydrogen that surrounds galaxies in a kind of halo. Hydrogen gas doesn't glow, so it isn't visible in optical telescopes, but it gives off a characteristic radio emission. This halo extends far beyond the visible limits seen in optical telescopes, and it encompasses a volume that may be 10 times greater than the region of visible stars. And it turns out that the halo is also rotating much too fast. So the missing mass extends way beyond the field of stars. The only possible conclusion is that galaxies contain far more mass, typically 10 to 100 times more mass than the visible stars would suggest. This discovery is called the missing mass, or the dark matter problem. Vera Rubin likes to quip that it's not good for an observational astronomer to discover that most of the mass in the universe is dark. Well, the question arises, what is dark matter? First, we can be pretty sure what it isn't. Dark matter doesn't seem to be ordinary dust or gas, because that much material would block out most light from a galaxy. One of the most obvious possibilities, then, is a group of familiar objects called MACHOs, or massive, compact, halo objects. These are things like planets and brown dwarfs, comets, asteroids. However, all these objects should emit some heat radiation, yet the infrared satellites don't detect anywhere near enough of these objects to make up 90% of a galaxy's mass. Now, massive black holes are another intriguing candidate. However, such objects should act as strong gravitational lenses that occasionally pass in front of more distant stars, causing them temporarily to brighten, to twinkle. Star surveys that monitor intensities of tens of thousands of stars just don't see enough of these lensing, flashing events to explain dark matter in this way. There are other possible sources, but they require more of a hypothetical nature. It now appears that neutrinos have mass, for example, so they'll add to the dark matter budget. Other astronomers evoke what are called WIMPs, weakly interacting massive particles, for which there's no direct observational evidence at all. The fact is, we just don't know what mass is causing galaxies to rotate so fast, and this is one of the really exciting frontiers of science. We have a strongly supported theory of how the universe began. But can we guess how it's going to end? And here, too, studies of galaxies provide clues. Predicting the future requires playing our tape on fast forward. The ultimate fate's going to depend upon a balance between the present expansion and the force of gravity, which must be slowing down that expansion rate. So we can envision 3 possible scenarios. If the universe doesn't have enough mass, it's going to continue to expand forever, becoming more and more spread out and growing gradually colder and colder. Ultimately, when all the stars have formed and died, the universe would cool to a uniform temperature. That's a phenomenon called the heat death of the universe. Such an ever-expanding universe has been called an open universe. And I think most physicists find this scenario aesthetically unappealing, though some astronomers I've talked to really don't have a preference one way or another. They just say it is what it is. Now, a second possibility is that the universal expansion might gradually slow down, but never quite stop in what's called a flat universe. This result requires that the total mass of the universe exactly balance the expansion rate. Some scientists favor the elegant symmetry of this model. And then, if the universe contains more than a critical amount of mass, the expansion will eventually slow down, stop, and then reverse itself. The universe is going to get denser and denser. The wavelengths of cosmic background radiation will get gradually shorter. The universe will ultimately collapse back onto itself in a big crunch. This third possibility provides a kind of steady-state mechanism by which the universe can go on forever in a never-ending cycle of bangs and crunches. As of now, the open universe seems the most likely model. In fact, it appears the universe is expanding much too fast to ever slow down and stop. But keep watching science news. That's one